Today we're going to talk about magnetic force. So up to now, what we've said about a magnetic field is, well, what it does is it a compass points in the direction of the net magnetic field, and so we're going to explore that a little further. Where we are in our sort of landscape of electricity and magnetism is something like this. The big idea is that charged particles create fields, both electric and magnetic fields. And those fields made by charges, they affect other charges. And we've now seen several ways that charges can make fields and affect other charges. So if we have the sources here, how they charges create fields and how fields affect charges. If we make a table, if we have a charge that's not moving, we know that it makes an electric field. So, and we know that the electric field of a point charge is given by the equation. It's a vector. It's 1/4πε0 q over r squared in the direction of r hat. And that the force on some other charge due to this field is just that the charge of that charge times the electric field. We also found, so this is a stationary charge. We also found that a moving charge, so a charge that has some velocity, makes a magnetic field. And the magnetic field for a single point charge was given by μ0/4π, another constant. The charge times the cross product of its velocity with the unit vector in the direction of the vector r over r squared. And here's what we're doing today. We're going to be talking about how magnetic fields affect other charges. Now, of course, there are things other than point charges. And so how do we figure out the field of something other than a point charge? Well, we just use the superposition principle. And add up the fields, and we did the same thing with magnetic field. Now, just for completeness, a little bit later, we'll find out what accelerated charges do. So charges whose velocity is actually changing, and that'll be kind of interesting. So the basic idea behind magnetic forces is that it's an interesting one. Magnetic force only affects a moving charge. And the force on a moving charge, so if we have a charge, say a positive charge with a velocity in the plus x direction, and we've got a magnetic field due to some other charges moving through coils, perhaps somewhere here. We find that the magnetic force on this charge is perpendicular to both the velocity of the charge and to the magnetic field. So the magnetic force is and if we have a different situation, suppose we had a negative charge moving in the same direction with the same field. We'd find that the force on that negative charge is still perpendicular to both V and B, but it's in the opposite direction. And that suggests to us a cross product, and in fact, a cross product that involves the force that involves both velocity and magnetic field, but also has to include the charge. And it turns out that the mathematical expression for magnetic force on a moving charge is actually fairly simple. It's equal to Q V cross B, where B is the magnetic field in the region, V is the velocity of the moving charge, and Q is obviously the charge of the charged particle, and that's a sign quantity. It can be positive or negative. So we'll add our magnetic force here to this table. And that's a fairly simple expression. So let's actually try thinking about thinking through a problem here. So here we have a moving proton. Its direction is, the direction of the proton's motion is given by the vector v. In this region, there's a magnetic field shown by the cyan arrow. So that's vector b. And how do we figure out the direction of the magnetic force on the proton? So take a minute and think about this and see if you can figure it out, and then we'll work through it together. Okay, so as I hope you've been thinking, we can get the direction of a cross product. We're trying to get the direction of, remember that the magnetic force is Q V cross B. So the direction of V cross B we get by pointing the fingers of our right hand in the direction of V, and then curling our fingers toward B. And we have to orient our hand in such a way then that our thumb ends up sticking into the page. So V cross B is into the page. And we have to take into account the sign of the charge. Since this is a proton, it's positive. So QV cross B is also into the page. So the direction of the magnetic force is going to be in the minus Z direction. Questions about that? Let's try a different question. An electron is traveling in, and now it's an electron, so we have to be careful about this. We have an electron. It's traveling in the negative y direction. At the location of the electron, there's a magnetic field in the negative z direction. What's going to be the direction of the magnetic force on the electron? So remember that we have the magnetic force is QV cross B. So the first thing to do is get the direction of V cross B. We point our fingers in the negative y direction. We curl them into the page in the negative z direction. And so our thumb sticks out in the plus x direction. So we have V cross B is plus x, but Q is less than 0 because it's an electron. So QV cross B ends up being in the negative x direction. So we have a proton traveling in the negative x direction. So we have proton traveling in the minus x direction. It experiences a magnetic force in the negative z direction. What's a possible direction of the magnetic field at the location of the proton? So the question is, if we point our fingers in the minus x direction, and then we turn our hands so that our thumb points into the page in the negative z direction, it seems like we would have curled our fingers toward the plus y direction. So presumably we'd get here plus y. But why does the question say what's a possible direction of the magnetic field at the location of the proton? Why doesn't it say what is the direction of the magnetic field at the location of the proton? The answer is that the magnetic field certainly could have been in the plus y direction. So we get V cross B in the negative z direction. But what if the magnetic field had a component in some other direction? So what if the magnetic field had a component that was in the minus x direction also? Note that we'd still get the same force because the component of B in the x direction in the direction of motion, doesn't actually affect the moving proton. It's only the component perpendicular that affects it. So as long as the magnetic field has some positive y component, then we'll get the force in the negative z direction. Questions about that? Could I draw the coordinates on the last example? They're the usual ones, sure. It's plus x plus y and z out, right? So the proton's traveling in the minus x direction. Okay, so the right-hand rule. So how did I do that? So the idea is that the right-hand rule, so we want to point to evaluate force is QV cross B. This is the same old right-hand rule we use for every vector cross product, where it's you point your fingers in the direction of using your right hand, your fingers in the direction of whatever the first vector in the cross product is. We'll call it vector 1. And then curl toward vector 2, whatever the second vector in the cross product here. Here, this is the first vector, and that's the second vector. And therefore, our thumb should stick out in the direction of the final answer. In a question like this, where you're sort of reverse engineering a cross product, you actually have to do a little trial and error. If you point your fingers along the direction of your right hand in the direction of V with your palm down, you'll discover that your thumb sticks in the plus C direction, which isn't what you want. So you have to rotate your hand over so your palm is up, so your thumb sticks in. Okay? So evaluating the cross product, we've QV cross B. Well, we can use the right-hand rule for the direction. And the magnitude is, of course, the magnitude of QV cross B, which is absolute value of Q, magnitude of V, magnitude of B, sine of theta, where theta is, of course, the angle between V, let's try that again, V and BE, and this angle is theta, and theta is always the smaller of the two angles. So let's go back to the first situation where we had a proton whose velocity would look kind of like that, and we had a magnetic field in that direction. And let's say that this angle is 140 degrees. And let's say that the speed is 2 × 10⁵ meters per second. The magnetic field is 4 Tesla, and the charge, it's a proton, so it's 1.6 × 10⁻19 coulombs. Then the magnetic force, F is equal to 1.6 × 10⁻19 coulombs times 2 × 10⁵ meters per second times 4 Tesla times the sine of 140 degrees, and we get 8.2 × 10⁻13 newtons. Now, one thing to consider, another note just to note, suppose we have an electron traveling in the -y direction, and there's a magnetic field also in the -y direction. What's the magnetic force on this moving electron? Well, of course, the magnitude of the force is 0, because we have Q V be sine of 0 degrees, and that's a 0. So if the magnetic field is in the same direction as the motion, nothing happens, because the magnetic force has to be perpendicular to both V and B. Yep, that's right. So questions about this piece? And of course, we can use the exact, if we have the V and B as vectors, we can actually evaluate the cross product using vectors also. So let's think for a minute about what would happen, what the path, so what would the path of a charged particle in the magnetic field look like? When the force is always perpendicular to the motion. So let's go back to the momentum principle, our favorite principle. So P in the future is the initial momentum plus F net delta T over some small time step delta T. So let's consider a proton, say, that starts out initially with a velocity in the y direction, in a situation where in this region there's a uniform magnetic field out of the page. So in the plus z direction. So at this instant, we're going to have V cross B, the magnetic force is going to be in the plus x direction. And that means that we'll have, when we apply the momentum principle, here's our initial momentum. And now here is, let me draw it on the other side so this doesn't get so messy. So here's our initial momentum. And now we add an impulse. So we add an F net delta T. And so our new momentum is now in that direction. Call that delta P. Well, so the particle moves this way for a while, and now it gets to here. And it's moving here with momentum. Now its momentum is in this direction. But now we have a magnetic force that's perpendicular to both its momentum here and the magnetic field. So the magnetic force ends up having to be now in this direction. And that means that the change of momentum is in the direction of the force, and we get a new momentum here. And you can see what's going to happen. We do it again. Here's the particle now. It moved that way for a short delta T. Now here's the momentum. But now the magnetic force has changed direction because it has to be perpendicular to the velocity. So now the magnetic force is this way. And therefore, the impulse is like that. We're going to turn the momentum again. And you can see that the particle is going to end up traveling in a circular arc. Because now, why is it an actual circle? Well, since the magnetic force is perpendicular to the momentum, it just turns the momentum, but it doesn't change the magnitude of the momentum. So the magnitude of the magnetic force is constant, so we get motion in a circle. And the lab you're going to do this week, a computational lab, involves modeling the motion of a charged particle in a magnetic field. The way lab is going to work this week, this lab is intricate. The way lab is going to work this week is that I will post the lab for everybody after this lecture, and you can work on it on your own time. The TAs will be available on Zoom during your scheduled lab sessions for help, and I will try to be there also, so that if you need help or you want to ask questions, you can come there. It will probably be most efficient if you've had a chance to look at the assignment before these lab sessions and actually work through a little bit of it, at least to get to the point where you have questions, so you can ask for help. And the lab will be due, let's say a week from today, actually. So give you time to work on it. Yeah, you still say your name for attendance, please. Now, since we've got a circular orbit here, we can actually predict some things about the orbit. Remember that for curving motion, we had last semester, we derived the fact that the perpendicular component of dp dt, was equal to the absolute value, the magnitude of this was equal to PV over the radius of curvature. So and that at low speeds, if v was less than c, that was equal to mv squared over r. But this is also equal to the perpendicular component of the force acting on the moving object. Well, in this case, the perpendicular force acting on the moving object is a magnetic force. So we can rewrite this relationship as mv squared over r equals qvb sine of 90 degrees for this circular motion. And simplifying that, we get mv over r is equal to qb. And we can solve that in various ways. One thing we can do is solve for the radius of the orbit, which is going to be mv divided by QB. This is actually a magnitude of Q. So the radius depends here, depends on the ratio of the mass of the object to the charge of the object. This actually, we can look at a little later if we have time, but this is actually how a mass spectrometer works. In a mass spectrometer, charged particle, parts of an object, of an atom, or even some sort of molecule is ionized by knocking off an electron, and then accelerated through a potential difference. And then there's a magnetic field in the region through which it travels. And so it curves around and eventually hits some detector. And since the radius of the orbit depends on the mass to charge ratio, and you mostly are going to get singly ionized things, you can figure out the mass of your fragment or your atom by looking at the radius of the orbit. Now we can also figure out the period. So this is the radius here. We found the radius depended on m over q. What about the period? Well, remember that, and for that matter, the angular speed. So remember that the angular speed of, and this is in radians per second, of an object traveling in a circle is equal to v over r. Where does that come from? Well, the distance it travels, 2 pi r, one complete orbit, is equal to its speed times the period, the time it takes it to get around. So 2 pi r over v equals the period. The angular frequency is, angular speed is 2 pi over the period. So that's 2 pi divided by 2 pi r over v, and that gives us a v over r. So, so going back to our original derivation up here, so we have dp dt perpendicular was equal to pv over r, and we can rewrite that as omega times the momentum. And that's equal to the magnetic force, QVB sine 90 degrees. And so the angular speed is just going to be equal to QB over, well, over what? Well, notice that omega times p is equal to omega times a gamma mv, and that's equal to a QVB sine of 90 degrees. So omega is actually going to be equal to QB over gamma times the mass. So the angular speed in radians per second. And that's actually true relativistically as well, if gamma is greater than 1. The period is equal to, so this is 2 pi over the period is QB over gamma m. And so the period ends up being 2 pi m over the charge times the magnetic field. Now, what's interesting in both of these results is notice that what it doesn't depend on. The period does not depend on V, and it does not depend on R. So all it depends on is the mass, the charge, and the magnetic field. And up here, so that's actually a fairly interesting result, and this result is one of the key facts that makes cyclotrons work. And if we have time, we'll talk about how a cyclotron works. Okay, so clearly, if there are magnetic forces on moving charged particles, then a current carrying wire ought to experience a magnetic force. So here is a video demonstrating force on a current carrying wire.
So I have here a large magnet, south pole, north pole, so the field is pointing up. And then I have a big, copper tube, which is connected to the wires here and there. When I connect these here, electricity will flow through this guy, through the red, through the copper tube, and then up through ground, and then back home. So we'll have electricity flowing this way, magnetic field pointing up. We expect a force inward. And sure enough, we get an inward force. Now, if I reverse the direction of the current, we expect an outward force. Get this guy out of the way. And there you see it.
So when he talks about electricity flowing, he's talking obviously about direction of conventional current. So conventional current was flowing that way. So notice that he was using a pretty big battery, looked like a 12-volt battery with large wires to get a big effect. And in fact, if you try this with the batteries and wires and the magnet you've got in the electricity kits in lab, the effect is fairly small. You can see the wire move, but you have to look quite carefully. So the reason he was getting a big effect is he had a big current and a huge magnetic field. So it's not big, but it's there, it's really there. So we can derive an equation for the force on a wire, on a current in a wire. And it's going to look really familiar. So in some section of wire here, if we have a piece of wire of cross-sectional area A and length delta L, the force on the wire is just going to be the number of moving charges in that piece of wire. times the force on 1, which is going to be equal to QV cross B. And we're going to here, of course, use conventional current. So we're going to assume Q is positive. And we're going to call this delta F because it's the force on one piece of wire. Well, so all we have to do is figure out the number of moving charges in that piece, and that's just the mobile charge density. Number of mobile charges per cubic meter times the volume, which is the cross-sectional area of the end, times the length of the cylinder. So that's the volume of the cylinder. Times QV cross B. And we're going to play the same game we played before, where we say that we write the drift speed of this fictitious positive charge is equal to the drift velocity, rather, is equal to the speed times the unit vector in the direction of the drift speed. And so we're going to rewrite this length delta L times V drift is going to be equal to delta L magnitude of V hat. And we're going to regroup so that we combine the length of the wire and the direction of motion into one thing, which we're going to call delta L vector. And so we end up now this expression looks like the speed times the vector delta L. And so once we do this, we can rewrite this as we have a Q and a V delta L cross B, where now delta L is a vector in the direction of conventional current. So the expression for the magnetic force on a piece of a wire, some length of wire, is just going to be, well, that's the conventional current. So we have I delta L cross B. So if we have a wire here with conventional current in the direction of the red arrow, and there's a magnetic field in this region that's in the minus C direction, so it's into the page here. What's the direction of the force on the wire going to be? Think about that for a second. So we have the vector delta L in the direction of I. We have the magnetic field into the page. And so using our right hand, point the fingers in the direction of delta L, curl into the page. Our thumb sticks up in the plus Y direction. So the magnetic force on this current carrying wire should be in the plus Y direction. Now, an interesting thing to think about is how we would calculate the force that one current carrying wire exerts on another. And so if we have a wire with a current going this way and another wire with a current going that way, what's the direction of the force on the bottom wire? Well, this is a two-step problem. First, we have to figure out the magnetic field. So steps. We have to find B1 at location of wire 2. So the magnetic field made by wire 1 at the location of wire 2, and then use I2 delta L to cross B1 to get the force. So let's see. Going back to predicting directions of magnetic fields, we have a current going this way. So remember that we had for the equation for magnetic field of a current carrying wire was a IDL cross R hat over R squared times mu 0 over 4 pi. So we have delta L this way. Our observation location is down here at wire 2. So this would be R hat. So DL cross R hat is into the page, which means that the magnetic field down here produced by the top wire is into the page. And therefore, now, so we've done step 1, now step 2, we have delta L2 here, conventional current in this direction. So we have delta L2 cross B1, so plus X cross minus Z is going to give us a force in the plus Y direction. So it looks like wire 2 is actually attracted to the current in wire 1. What's the situation going to be at wire 1? Well, what's the magnetic field made by wire 1 at the location of wire 2? So we have here, we've got a delta L2, we have, not squared, we have an R hat 2, delta L cross R hat. Looks like that magnetic field would be out of the page. And so now we can apply this second equation to get the magnetic force. Delta L cross B is now going to give us a magnetic force down. So it looks like two current carrying wires with currents in the same direction would actually attract each other. So how would we do this numerically? Well, the magnetic field of wire 2, if it's a long enough wire, is approximately mu 0 over 4 pi 2I over the distance. We'll call this distance here D. So force on, sorry, let's make that be 1. Force on 2 would be I2, the length of wire 2, delta L2 times B1, sine of 90 degrees. And if we substitute that in, we'd have an I2 delta L2 times a mu 0 over 4 pi 2I1 over D, which would give us the answer. So suppose, just to get a number, suppose I1 is I2 is 10 amps, D is 1 centimeter. The length of these wires, each one is 1 meter long. So what we'd get would be, let's see, we'd have 10 amps times 1 meter times 1 times 10 to the negative 7 Tesla meter per ampere times 2 times 10 amps divided by 0.01 meters. And so we have 100 divided by, so it's going to be about, it's not going to be a very big force, is it? Something like, okay, 10 times 100, that cancels, something like 1 times 10 to the minus 7 newtons, actually. Which is why he had to use a big magnetic field and a big magnet in that video to get a force. So I want to talk a little bit about what happens if there are both electric and magnetic fields in a region. So we'll consider this situation where we have not only a positive charge moving to the left, we have an electric field down, and we have a magnetic field out of the page. So now there are going to be both electric and magnetic forces on the moving charge. So what's going to happen? Well, we work it out and add them up. So the electric force is clearly going to be down because it's a positive charge. So the force is in the direction of the electric field. Magnetic force will fingers along V, curl out, thumb up. Magnetic force is going to be up. And so the net force is just a question of the relative magnitudes of those two forces. Let's consider a similar situation. But now exactly the same field configuration. But we have a negative charge moving to the left. So now the direction of the electric force is going to be up because the charge is negative. The direction of the magnetic force is going to be, well, V cross B is up, but now it's we have to multiply by a negative number, so the magnetic force is down. So both forces reverse their directions, and the sum again will depend on the magnitudes of these two forces. So the question we want to ask here, though, is could the net force be zero? Well, sure. If the electric force is equal to and opposite to the magnetic force. So how would that happen? Well, if F net now we have the magnitude of the electric force is the magnitude of the magnetic force. So we have QE equals QVB sine of 90 degrees here. The Q's cancel, sine of 90 degrees is 1. So we would have the electric field is equal to the speed of the moving particle times the magnetic field. And what would the path of the particle be in this case? The particle would just move at a straight line at constant speed, since the net force on it is 0. Now notice that this is really interesting, because so if we have a situation where the electric field, the magnitude of the electric field is exactly equal to the speed of the particle times the magnitude of the magnetic field, then F net is 0. Now notice that this works for positive or a negative charge, although the directions of the individual forces were reversed, the net force was the sum, and so that could still end up being 0. And the condition depends only on the speed. So what would happen if a particle came in with a speed? So we set up these fields so that E is equal to VB, and a particle comes in with a speed that's different from E over B. Well, it would bend one way or the other. So we have V, the particle would go straight through. So V is equal to E over B. But if V is not equal to E over B, it would bend one way or the other, depending on. This configuration of fields, this configuration of crossed E and B fields, is known as a velocity selector. And it can be used to select for particles moving at a particular speed, whether they're positive or negative, because only particles with the right speed get through in a straight line. And everything else is deflected down and hits something else. And notice that it works equally well for positive or negative charges, because as long as these fields are balanced that way, then the particles can go right through. So let's do a quantitative example here. Suppose we have a magnetic field out of the page, an electric field down, and we have a particle, negative particle, traveling this way with speed v. Let's say that the electric field is 10 to the third volts per meter. A magnetic field is half a Tesla, which is a big field. And the charge of the particle is, it's a doubly charged ion. It's minus 3.2 times 10 to the minus 19 coulombs. So what's the speed at which the particle would travel in a straight line? Well, we want QE to be equal to QVB sine 90 degrees. So V is equal to E over B. So that's 10 to the third volts per meter divided by 0.5 Tesla. So that would come out to 2,000 meters per second. So if a particle was traveling, charged ion was traveling 2,000 meters per second, it could go right through. So those of you who've taken chemistry courses may have actually used a mass spectrometer in your chemistry courses. And here's a diagram of a simplified mass spectrometer. So what happens here is that particles start here, and they're ionized usually by bombarding with electrons and then now that they're charged, we can put a potential difference across these two big plates here to accelerate them so they get up to a fairly high speed. Then they enter a region where there's a magnetic field in the grayed out region. There's a magnetic field through this gray region that's uniform. But there are also some deflection plates here. So there's a potential difference, delta V2. So the deflection plates make an electric field up or down in that region. And if the speed of the particle is the correct speed, if it's been accelerated to the correct speed, it'll travel straight through this region, and then it'll curve around, so it hits the detector because the magnetic field is making it curve. But if it doesn't have the right speed, it'll crash into one of the plates and it won't get through. So so in a mass spectrometer of this kind, you'd ionize something, get it up to a given speed, it would go through some deflection plates, and then in a region where there's a magnetic field, it would actually curve around and hit a detector. So how does a quadrupole change the path of a particle? So Tristan knows that that quadrupole magnetic fields are used to actually focus particles, and this is true in accelerators too. So magnetic, what's a quadrupole? Well, we know what's a dipole. So a dipole is when you have an electric dipole is just a positive charge and a negative charge. An electric quadrupole would be something like this, where you'd have 4 charges. A pole in this case just refers to a charge, for example, and it makes a more complicated field. A magnetic dipole has got a north end and a south end. So a magnetic quadrupole would be magnets in coils arranged in such a way that you'd get something like this, making a field that can be used to take a beam of particles and either make them, to collimate them by making them converge or diverge, depending on what you need to have happen. And the details you'll need to sit down and think about, but that's the way it works.